Hey guys! Good morning, afternoon, good evening, and welcome to statistics. Alright, so we are working on section 2 of chapter 7 today, which is estimating a population mean. So essentially in this section we're doing the exact same thing as we did in section 1. It is just for means instead of proportions. But really we're doing the same thing. We are using our sample mean to try to estimate our population mean, right? And remember, for sample mean, we use our x bar, and for our population mean, we use mu. So doing the exact same thing here, right? We're using our sample mean, our x bar, as a point estimate for our population mean, mu, right? And that is because your sample mean targets your population mean. Right, your sample mean is an unbiased estimator of your population mean. So we're going to use that x bar for our confidence interval, right, for the middle of our confidence interval. And then again, we're going to calculate some margin of error, which we're going to both add and subtract to x bar to get our confidence interval. And similarly to our first section in chapter 7, we are also going to calculate the sample size that we need for a population mean. All right, so just refreshing our memory here with our notation, right? Mu is population mean, n is sample size, x bar is our sample mean, e is our margin of error, and s is our sample standard deviation. So some requirements when we are creating our confidence intervals. First of all, we need a simple random sample, and then we also need either the population to be normally distributed or we need the sample size to be larger than 30, right? Where do those two conditions come from? Right, those come from our central limit theorem, which involved means, right? So we still have those same conditions here. Now, when we are calculating our margin of error, we are doing that a little bit differently here, okay? And yes, again, we can use our calculator, right? In order to get our confidence intervals, we don't need to do it by hand, but I think it's a good exercise to do it by hand at least once, right? Just like in 7.1 when we were estimating our population proportion, right? We calculated our margin of error by hand and added and subtracted that to our p hat. Right, and we also practiced using our 1 prop z interval. So in this section, we are going to calculate our margin of error by hand, right, and add and subtract that from our sample mean. And then I will also show you how to find your confidence intervals for your means right in your calculator. Okay, and it's fine with me if you always use your calculator. I think it's just always a good idea to practice by hand once so you can at least understand where those values are coming from. All right, so first of all, you may notice something a little different here, right? Instead of a z sub alpha over 2, we have a t sub alpha over 2. So this is a critical value, but this is a t critical value, and it's a little bit different, and I will explain. Right, then we'd be multiplying by our sample standard deviation and dividing by the square root of n here. Over here, this says df equals n minus 1. df stands for degrees of freedom, right? To find your degrees of freedom, you take your sample size and you subtract 1 from it, right? So if we had 25 as a sample size, our degrees of freedom would be 24. Okay, and this is going to come into play when we are finding our critical t value, which I will explain in a moment. Still, we have our confidence, when we're creating our confidence interval, it's associated with a particular confidence level, right? And the most common confidence level is 95%, right, or 0.95. And remember, some of these problems will give you that confidence level. Other problems will give you your value of alpha, right? But your confidence level and alpha are complements of each other. So 1 minus alpha gives you your confidence level, and 1 minus your confidence level gives you your value of alpha, right? So you can keep going back and forth there. All right, so critical T value, okay, is a critical value like our Z critical value is, right? The only difference here is that it is using what is called the student T distribution, okay? So let me explain that a little bit here. So the student T distribution is a normal distribution, but it looks slightly different. So let me show you a picture first here. So if you noticed over here, I've drawn 3 different student T distributions, okay? And there's not just one like there was with our normal distribution. The thing about the student T distribution is that it is dependent on the sample size. So for different size samples, the distribution is going to look slightly different, okay? So if you can see here in green, the normal distribution tends to be a little bit higher at the peak and a little bit lower over here at the tails, right? When we're dealing with the student T distribution, the higher our value of n is, the closer it will be to a normal distribution. And the smaller value of n, it's going to be a little bit further away. Okay. In general, it's a very similar shape, but we do need to calculate our T critical values instead of our Z critical values. And just to be clear, the reason why we are doing this is because we very, very rarely know our population standard deviation. Okay. If we knew our population standard deviation, we would be able to use a standard normal distribution just like we did with our proportions. But typically in cases when we're involving the mean, right, if the whole kind of point with this chapter here is that we don't know anything about the population, right? We don't know the population mean or the proportion or the standard deviation. We don't know anything about the population. And we're trying to take a sample and calculate a statistic on that sample and use that to create some sort of estimate, right? Some sort of interval for which our population parameter fits within there. Okay, so when we are trying to estimate our population mean, right, it's very, very rare to have our population standard deviation. So instead of using a standard normal distribution, we need to use a student's T distribution. Okay, it's very similar, but slightly different, right? A little bit lower to peak and a little bit higher over here on our tails. Okay, and again, this student T distribution is dependent on our sample size, and we need to input what's called the degrees of freedom. So we use the value of the degrees of freedom to help us calculate this critical T value. So, and again, your degrees of freedom is just one number smaller than your sample size. All right, so let's see. I think I've talked a little bit about these things already, but feel free to pause here and read over the student T distribution to see if it helps. The main idea is that we don't have our population standard deviation, so we have to use this student T distribution, which is slightly different than our normal distribution. All right, so again, degrees of freedom, right, is one number less than your sample size, right, and this is what we are using to help find our critical T value, right? And critical T value, it's still, when we draw, our distribution, it's still in the same place, right? It's still off to the right here, separating this, alpha divided by 2 area, okay? All right, and I just wanted to mention, we are not going to be calculating any T-scores here, but I did want to point out that this should look very, very similar to our formula for Z-scores. The only difference here is that this is involving the sample standard deviation, right? This is involving our S here instead of our sigma, right? And that's the whole difference between our student t distribution and our normal distribution. Normal distributions, we know what our population standard deviation is. Our student t distribution, we do not know what our population standard deviation is, and that causes there to be a little bit of a wider distribution. Okay, so let's actually jump in here to talking about our critical value. So similar to z-scores, you could also use a table. I'll briefly show you one example with the table, but I personally never use a table. I don't use a table for z-scores, and I don't use a table for these t-scores either, right? For critical values, whether it's a t critical value or a z critical value, I don't use them. I prefer to use my calculator because it gives me an exact answer, and I find it a bit easier, right? Tables, you sometimes need to approximate, and for that reason, I prefer my calculator, but I will briefly show you both here, okay? So if we were using a table, we would, right, you can find this either in your textbook or you could just Google critical t values. Okay, so you would go to the degrees of freedom, right? So if the sample size was 15, your degrees of freedom would be what? Right, it would be 14. So you would go down here to 14. Okay, so you'd go down to 14. And then you'd also have to be given information about your confidence level or your alpha value. So let's say, for example, that they told us that we had a 90% confidence level, right? If we have a 90% confidence level, that means that our value for alpha is going to be what? Right? It's going to be 0.1. So alpha would be 0.1, and that would mean that our alpha over 2 would be 0.05. Right, so if we were to sketch a little picture here, right, our confidence level would be 0.9, right, so we'd have 0.9 in the middle here, which means we'd have 0.05 to the left, and we'd have 0.05 to the right. So again, for the example of n being 15, we would have 14 degrees of freedom, right? And the area in one tail would be 0.05. So we'd go over, right, area in one tail is 0.05 here. And so we would see our critical t value is 1.761. Right, so here we would say that our t of alpha over 2 equals 1.761. All right, so this is how I use the table. I'm not going to focus so much on the table because I would prefer to use our calculators. All right, so in the calculator, right, to find z-scores, what did we do in our calculator? Or z critical values? Right, we used inv-norm. So to find our t-scores, our critical t values, we are going to be using inv-t. Okay, inv-t is right below our inv-norm. So if you go to second and then vars, you should see your inv-t right below your inv-norm. I will say that some of the TI-83 calculators don't have the inv-t in it, but you can very easily program that. So I will send you guys a link on how to do that. It'll probably take you 10 minutes on YouTube, and I can also help you with that. So let me just show you while I'm here on my calculator. So I would be going to second and then vars, right? And you see right below inv-norm is our inv-t. Okay. So let's do the same example I just gave us a moment ago. So we said that area in the tail was 0.05, right? And we had 14 degrees of freedom, right? In other calculators, you may need to type it in this way, right? Your inv-t with your area to the left there, and then comma and your degrees of freedom, okay? Remember, this is going to give us a negative value because technically this right here is our area to the left. But just like our critical z values, our critical t values are always going to be positive. So we'd have positive 1.761. Right, so we get the same exact answer. So it's really up to you if you would like to use your inv-t or if you would prefer using the table. Either way works. All right, so again, either inv-t or using the t-table, either way works. I prefer using inv-t. If you have any questions about it though, please do ask. All right, just remember we're putting in the area to the left and then the degrees of freedom, which is one number smaller than the sample size. Okay, but you need to remember you always need to change it to a positive. Our critical values are always positive here. All right, so please pause this and take a minute and find your critical t value for a 95% confidence interval. All right, so if we are doing that, right, we know that 1 minus alpha is equal to 0.95. So alpha is equal to 0.05. So alpha over 2 is equal to 0.025. So now in our inv-t here, I would be plugging in 0.025. And since our sample size is 15, our degrees of freedom is 14. All right, so we'd have 14 here. All right, so now let's go to our calculator. So again, we're going to go to second vars, go down here to our inv-t. Now we have an area of 0.025, degrees of freedom 14, and here we go, negative 2.145 if we're rounding to 3 decimal places. And what else do we have to be careful about here? Right, we need to make our answer positive. So this would be equal to, right, this is equal to negative 2.145, but we would say that our actual critical value here is positive 2.145. Right, and if you wanted to, you can also do this in the table, right? So again, we would have 14 degrees of freedom, but now our area in one tail is 0.025. So we'd come down here and we would get 2.145. All right, so you can do it with your inv-t or you can do it with your table, whatever way floats your boat. Okay, and I do want to mention quickly here, if it helps you to draw your distribution to think about the areas, please do that. Right, so if we have our distribution, if we have our terrible distribution here, right, we know that this middle part has to correspond to our confidence level. So this would be 0.95, right? So that's 95% here. We have 5% left, right? So split that evenly, and each of these sides has to be 2.5%, which is the same thing as 0.025. Right, so drawing yourself a little picture is always a good idea, right? Just doing all of this math without understanding it, not the best. Right, so please draw yourself a picture if you're getting a little bit stuck. All right, so now let's talk about constructing a confidence interval, right? And what we're doing here is we are using our sample mean, our x bar, as a point estimate for mu, for our population mean. So again, you are going to verify your requirements, okay? Typically, we do not know our sigma, we do not know our population standard deviation, and so we calculate a critical t value, right? I personally like using inv-t. If you'd like to use the table, go for it. Right, and we have to use our degrees of freedom, and we also have to use our confidence level. Okay. Next, we would be evaluating our margin of error. Right. Sorry if you can't see this right over here. right? This is an S divided by root n. So our margin of error would be equal to your critical value multiplied by the sample standard deviation divided by the square root of n. Okay. Once we have our margin of error, what do we do to find our confidence interval? Right, we add and subtract it to the sample mean. Perfect. So we'd be adding and subtracting that value to the sample mean. And again, when we're writing out our confidence intervals, there are 3 different ways we can do that. Whatever floats your boat is fine with me. Just kind of be familiar with either of them, right? You either have your inequality notation, you have your plus and minus notation, or you have your interval notation. Okay, and rounding, don't worry about it too much. I will always tell you what to round to. All right, so this would be our process by hand. And again, I just want to be clear, we are using our critical t value when we don't know our population standard deviation. Right? If for some odd reason we did know our population standard deviation, we'd be finding a z critical value instead, right? And I'll do one example with that later on. It really doesn't come up so frequently though. All right, so now for the calculator, how do we find our confidence intervals in our calculator? All right, so we would go to the same place, right? We would go to our stat, right? And then we would scroll to the right here to get tests. And then we'd scroll down to our t interval. Okay, so interval, we're looking for confidence interval. T, because we do not have our population standard deviation, so we have to use the student's t distribution. Okay, both of these intervals you use for means. The mean ones don't say mean in them, right? The other ones will say proportions and whatnot. All right, so again, we're using our t interval when we are trying to estimate mu, which is our population mean. Okay, and t interval, we use that when we do not know the population standard deviation. Okay. On t interval, when you click that, there are 2 different options here, right? There's a data option and then there's a stats option. Okay. The stats option you use when you're given statistics, right? When they give you the sample standard deviation and they give you some different stats, right? They're giving you the X bar, they're giving you sample standard deviation. Okay. You would be using the data button if they just gave you a whole list of data, and you would have to type the data first into your list. All right. So let's actually do an example now. Okay. And again, I think it's a good idea to do an example by hand and then also using the calculator. All right, so let's see. I would suggest you pausing here and giving this a shot, right? If we're doing this by hand, you first need to find your critical t value, right? And you do that by using the confidence level that they're giving you, okay? Then you would be multiplying by the standard deviation and dividing by the square root of n to get that margin of error. And from there, you're adding and subtracting to your X bar. Okay, so how about let us do that together here. All right. So we said that our confidence level is 90%. So that means 1 minus alpha is 0.9. So alpha is 0.1. Alpha over 2 is 0.05. We were also given that our n is 15 here. So in our inv t, we're going to be plugging in 0.05 and 14, right? Because 14 is our degrees of freedom. Okay, so let's do that in our calculator here. So, it looks like we have already done that, right? That was the value we did before. So our answer, so that's negative 1.761. All right, so this is negative 1.761. which means that our critical t value is positive 1.761. All right, now to get our margin of error, we take this critical t value here, and we need to multiply it by that standard deviation, which was 2.9, and divide by the square root of n. All right, so we type that into our calculator here. Let's do that. So we want 1.761 times 2.9 divided by the square root of 15. Perfect. So we get 1.3186. 1.3186. Okay, so now we have our margin of error. So now we would be adding and subtracting this to what? To our x bar, right? So our x bar was 30.9. So we would take 30.9 and we would add this value here. And we would take 30.9 and we would subtract this value here. Okay. And so our confidence interval for mu, let's see, if we add this, we should get 32.2. If we subtract this, we should get 29.6. Okay. So we'd be saying here that we are 90% confident that the population mean, or the birth weight of girls, is somewhere in between 29.6 and 32.2. Okay. So again, this is our confidence interval. All right, so now let's give this a shot here on our calculator. So we would be going to second vars. Oh, that's a lie. We would be going to stat, and we'd be scrolling to tests, and then we want our t interval, right? T interval is for getting a confidence interval for means when you do not know your population standard deviation. All right, let's see. First, we were given the stats here. So we were told that our x bar was equal to 30.9. Our S was 2.9. Our N was 15. And our confidence level was 0.9. All right, there we go. We got the same exact thing, right? We have our 29.6 if we round to one decimal place, and 32.2. So it's perfectly fine if you come and use your t-interval to find your confidence interval. I personally like doing it by hand at least once just to see how everything is functioning, and also getting some practice with this inv t, because it's always good to know how to calculate your critical t values. All right, so we have this part B here. So now we want to do this with all of these different numbers. So we would need to enter all of these in our list. So stat edit, we'd have 33 and 28, 33, 37, 31, 32. Nope, I messed up here. This was a 31, 32, 31, 28, no, 34, 28, 33, 26, 30, 31, 28. Okay. And just to be clear, it does not matter what order you enter these in at all. All right, so now we go to stat, scroll over to tests, then again we want our t-interval. Right now we would be selecting data since we put everything into our list. So we want to use our L1 list, right? Then our frequency, we just leave it alone as 1. Our sea level was 0.9. And then we calculate here. All right, perfect. So this is what you would do if you were given a whole bunch of data. This data was representing the same problem, right? This was still the weights of those newborn baby girls, right, in hectograms. Okay, so we should be getting the same confidence interval here, right? It's slightly off because there's some rounding going on. All right, so if you need to see more practice, please watch this again, right? Or feel free to ask me and I can show you guys some more practice problems. Okay, so let's see. Very similar to 7.1, it is also good to be able to find your sample mean and your margin of error given your confidence interval. Right, so if I give you that confidence interval, to find x bar, right, x bar, your sample mean is right in the middle of that. So again, you'd be finding the mean between two values. So you're adding and dividing by 2, right? Then your margin of error is half of the distance. So you'd be finding the total distance between your upper and lower confidence limits, and then dividing that by 2 to get the margin of error. Okay, so same exact thing to find your x bar and your margin of error from 7.1. So lastly here, we are going to talk about the sample size we need to be able to estimate our population mean mu. Okay, so interesting thing here, we are going to be using our z-scores, okay, and we are also going to be using a population standard deviation. Okay, so first of all, we need to use our z-scores because we don't know what n is, right? The whole point is that we're trying to find n. So we can't use a t-distribution, we can't use the student t-distribution if we don't even know what n is. So we need to use our z-scores. And you're right, sometimes we will not have sigma, and so we will need to estimate it. Okay, so this is the formula we are using to find our sample size, right? There's no magical button in your calculator, so you have to be able to use this formula, right? So finding your z critical values, just like we've done, multiplying it by the population standard deviation, which we may have to estimate, dividing by the margin of error, which the problem will give you, and then squaring that. All right, again, n is your sample size, so you always need to round up, right? This is the minimum sample size required, so we need to round up. Okay, so when we do not know sigma, there's 3 different things we can do. We can use our range rule of thumb to estimate, right, which is our range divided by 4. We could use some estimate from an earlier study, or we can start sampling and calculating our value of S and using that, and then replacing it as we continue to collect more data. So typically in problems, you will either be using your range rule of thumb, or the problem will provide you some estimate to use. Okay, I would say in a more real life sort of situation, we'd probably be doing the second thing, where we start collecting data and use the value of our sample standard deviation to help find what sample size we need. All right, so please pause this, take a minute, and just plug everything right on in to the equation. Oh, I see we need some more information here. So let's continue onward. So actually pause here, right? And please plug everything in. You want to find that smallest sample size that we need when trying to estimate our mean IQ score. All right, So let's do this together. So first we need to find our critical z value, right? So we have 1 minus 0.95. That's going to give us our value for alpha. So alpha is 0.05. So alpha over 2 is 0.025. And now we'd be using our inv norm, right? Because we're going back to our z-scores here. So we'd have 0.025, 0, and 1. All right, so we plug that in our calculator. Right, this will give us negative 1.96. But we need our critical value here to be positive. So this is going to be positive 1.96. All right, so now to get our sample size, we'd have our 1.96, right? And what did this problem tell us? Let's see, it is safe. We can use 15 as an estimate for our population standard deviation here. So we'd have our n times 15, okay? And then this is saying within 3 IQ points. So that means our margin of error is 3. Okay, right, we have to be careful here. 3 is not a percent, right? 3 is the number of points, right? When we're dealing with means, we can have values that are above 1, right? But when we did this for our proportions, those always needed to be decimals, right? Our E would always be a decimal when we're talking about proportions. It is not always going to be a decimal when we are talking about means, because our units for E are the units of whatever the values are that we're trying to calculate, right? So in the last problem, they were hectograms. Right here, they're IQ points. Okay, so let's see, we multiply all of this, and we need to square this. All right, from here, you just plug it straight in your calculator, and then you need to remember to round up. All right, so we got 97. So we need a sample of at least 97 statistic students in order to properly estimate the population IQ score, the mean population IQ score for stat students. All right, wonderful here, wonderful, wonderful. So last but not least, I wanted to briefly mention what we do if we are in the rare situation of actually knowing what our population standard deviation is. Okay, so I mentioned before we would go ahead and find a z-score instead of a t-score, and we'd be using sigma since we actually know what that is. Okay, in your calculator, you would be using your z interval instead of your t interval. Okay, all right. So let's do the similar problem with our birth weights of those girls in hectograms. Except now, let's say that we actually know that our population standard deviation is 2.9. All right, so again, if we were doing this by hand, we would find our critical z-score, which we've done it a lot for 95% confidence intervals, right? We know it's 1.96. We've done it so many times. Then we would multiply by our population standard deviation, divide by the square root of the sample size, right? And we would get our margin of error. Right, so we're essentially just plugging everything right into our margin of error formula here. So once we've done that, we would now take this E and we would add and subtract it to our X bar, right? So our X bar, let's see, was equal to 30.9. So we would take that 30.9 and we would add and subtract the margin of error that we got. All right, so here we have our confidence interval from 29.4 to 32.4. Right? Or like I'd said before, we could use our z interval. Right, so we would go to our calculator here. We would go to Stat, Tests, scroll down to our z-interval. Let's use our stats here. So our sigma was 2.9. Our x-bar was 30.9. Our n was 15. And our C level was 0.95. All right, so we calculate that and we get the exact same thing here, right? So our confidence interval would be from 29.4 to 32.4. So we would say that we are 95% confident that the true value for mu, right, for the mean birth weight of girls is somewhere between 29.4 hectograms and 32.4 hectograms. All right. So again, that was our z-interval, and we use our z-interval when we are estimating a population mean, and we're in the weird situation where we actually know our population standard deviation. All right. So if you have any questions about this, please do ask. And we really just need to practice. If you would like me to do some more examples with you, please let me know. Alrighty, have an awesome day.